Dear students, now I am going to teach a problem in free convection, especially in a vertical cylinder, that is external flow. We move to the problem. Here, a vertical cylinder has 1.5 centimeter diameter and 1.5 meter height and 180 mm in diameter is maintained at 100 degrees Celsius. Then, in an atmospheric environment of, say, that is called as a 20 degrees Celsius. Calculate the heat loss by the convection on the surface of the cylinder. Assume the properties of air may be considered as mm, properties of air at a mean temperature as a rho density, kinematic viscosity, specific heat, and thermal conductivity are given. Here, note that so in the problem, a cylinder have what 180 mm in diameter. So consider that is called as a 180 mm diameter and having a height of say that is a 1.5 meter. So its height is called as consider as that is called as is 1.5 meter and the diameter which is considered as say that is called as a 180 mm. Then the temperature is maintained, the plate temperature is maintained at say that is called as 100 degrees Celsius. So here the wall temperature that is a TW, that is wall temperature, is maintained as 100 degrees Celsius, and ambient air temperature that is a T infinity air temperature is maintained at what 20 degrees Celsius. So these are the given data. So 180 mm diameter, 1.5 meter height, and maintains 100 degrees Celsius of surface temperature and 20 degrees Celsius of air temperature. Calculate the heat loss by the free convection. So because of free convection, how much heat is lost in the cylinder? Listen, and also in the problem, assume the properties of air is taken as mean temperature is taken as some values that is given. But in the previous problem, we discussed in forced of free convection, the properties can be calculated on the HMT data, but here it is given. So what is the difference between these two? One is given, another one we are going to find. So listen, so we approach a problem. First we find the film temperature. There is a film temperature that is equal to T wall temperature, that is atmospheric temperature by 2. So here there is 100 plus 20 divided by 2. We are getting there is a film temperature is equal to 60 degrees Celsius. Okay. Then now it's a free convection, so there is external flow. First case, that is a free convection. Second one is that is called as that there is called as external flow. Then third one you are going to find the properties. Then properties is given in the table. Is given in the problem itself, so you no need to go move for the property table in the HMT data book. Fourth one, here air is surrounded. Fourth one, you are going to find the flow is a laminar or there is a turbulent. For this case, you are going to find the Kirchhoff number in the free convection mode. Here, so the Kirchhoff number you can be find out the Kirchhoff number is equal to there is a z beta then x cube into delta d divided by this is called as a nu square. Here you are going to find the beta. How we can find the beta? So beta that can be find that is a beta is equal to 1 by Tf, where Tf is in what Kelvin. So here the film temperature is equal to what? The film temperature is equal to 60 degrees Celsius. So which can be that is written as 373 plus 60, which is equal to 230 233 degree. So 333 Kelvin. Here the film temperature is equal to that is called as a 333 Kelvin. Then 1 by Tf set is equal to 1 by 333 Kelvin. We are going to find the film temperature, the beta that may be around, which is equal to 0.003 0.003 Kelvin power inverse. So that is called as a beta. So 0.003 Kelvin power inverse. That's a beta. Now we can substitute the beta in this equation. But in the problem, the standard value is given as excuse, but in the problem we can replace x in terms of the result because the boundary layer is formed that is along the towards the height of the cylinder. So we consider length HRL is considered. So this problem this can be rewritten as GR is equal to G beta then L cube into delta t divided by nu square. So you substitute the approximate G is equal to, say, that is 9.81 into beta, that is equal to 0.003 Kelvin power inverse into L, which is equal to what? There is a 1.5 meter. You have to return as there is a 1.5 whole cube into delta T. So delta T, which is equal to difference between this temperature, is 100 degrees Celsius minus 20 degrees Celsius divided by, there is a kinematic viscosity nu. So nu, that value is equal to 18.97 into 97 into 10 to the power of minus 6, that is whole square. After substituting the above values in the Grashof number equation, you may get the Grashof number value, which may be around, which is equal to 2.208 into 10 to the power of 10. So Grashof number, that is the only number, is not enough for finding the flow. That is enough for finding the flow is laminar and turbulent. So finding the laminar or turbulent, we need a GRPR. GRPR. So here GR is, you already find that is GR. How to find the PR? So in the previous problems, we taken a PR from the data book, that is from 60 degrees Celsius. But here the PR can be calculated indirectly in this problem. How we can calculate the indirectly? So how that is a found PR from the data book? Listen, right? So here in the data book, just wait. I think the system is not supported. Okay. The in the data book, listen. Sorry. Wait. So here, PR can be calculated by means of formula. You know that here the PR that can be found by means of that formula Prandtl number, so which is equal to ratio of, that is a specific Cp mu divided by, that is called Cp mu divided by K. In a problem, the thermal conductivity is specific, it is given. Then absolute viscosity, there is mu is not given, but you can calculate a mu from what? Directly from the density and kinematic viscosity. Then K is given. So instead of mu, we can substitute a rho V. How we can rho V? So there is a absolute kinematic viscosity is equal to absolute viscosity into density. So we need absolute viscosity mu is equal to density into kinematic viscosity. So finally, write this equation Cp into, that is a rho into that is mu divided by what? That is thermal conductivity. So this is the formula. Here, by this formula, we can find out the Prandtl number manually, and that we are also check with the property values at 60 degrees Celsius. Here, the air is the fluid. So, in a case of air, what may be the value for the Prandtl number? Just you note that. Please wait. Here, at a value of 60 degrees Celsius, this is the value. We are almost having a thermal conductivity is equal to 0.0896, but and then Prandtl number is equal to 0.696. We have a kinematic viscosity 18 minus, the same as the value given in the book, and density is equal to 1.060. That is also same as the given in the book. Now we are going to find there is a Prandtl number, so which matches the 0.696. That may be correct with respect to the value given in the book. Okay. Now we can into the problem here. Right. you can find out the GR, PR from the formula. So PR is equal to, that is equal to mu into Cp divided by thermal conductivity. So already we know that is the kinematic viscosity is equal to absolute viscosity by density. Here you can write the mu is equal to, that again mu can be written as, that is kinematic viscosity into density into Cp divided by thermal conductivity. Okay, so you can substitute the this is the equation for PR. So PR you can substitute in mu, that is mu, that the absolute viscosity is equal to 18.97 into 10 to the power of minus 6 into density 1.06 into Cp, that is given 1.004 divided by thermal conductivity K. So here the K is another one issue in this problem. What is another one issue in this problem? Here the K is not given directly in the watt per meter Kelvin. So here K that can be given in terms of watt per meter degree Celsius, but it can be given as kilojoule per meter or something. So now we converted into the values here, 0.1042 kilojoule into meter hour degree Celsius. So which can be written as 0.1042. For kilo we can write that is 1000 joule divided by meter. You have to place that. For hour you can be written as, it is equal to into 3600 seconds into degree Celsius. Finally, after substituting the above value, you may get the value which is equal to 0.02894 joule per meter second degree Celsius. Here 0.02894 joule per second can be written as watt. So watt per meter degree Celsius. So that is the thermal conductivity. In the problem it is given as K is equal to kilojoule per meter hour degree Celsius. So finally we can get the watt per meter degree Celsius. Substitute the value in this place. Finally we can get the Prandtl number may be, after substituting the K and all those things, we are getting the Prandtl number which is equal to 0.6975. This Prandtl number also matches with the table in the provided in the HMT data book. Thermal conductivity also matches with the data provided in the HMT data book. Finally, after substituting the GR/PR, so substituting GR and PR, so GR is equal to what? That is a 2.208 into 10 to the power of 10 into, that is a PR 0.6975. So we are getting the GR/PR, so which is equal to 1.54 into 10 to the power of 10. So that is a GR/PR. So GR/PR is equal to 1.54 into 10 to the power of 10. So we consider which is equal to greater than what? Greater than 10 to the power of 9. So flow is considered as what? Turbulent. So because it is greater than 10 to the power 100. So we find the column in the turbulent condition. Listen, here in the formula, in the HMT data book, in the free convection column, free convection column, it's a free convection. So in a free convection column, the flow is turbulent. Here there is a turbulent GR by raised 10 to the power of 9. The most generally used is equal to n.0110 to GR/PR whole power 0.333. So now we can enter the, given the problem which is in the table here. So Nu is equal to 0.10 GR/PR whole power, that is 1 by 3. This is the most commonly used Nusselt number to find in the vertical cylinder or surfaces. That value is that values which is equal to turbulent, because the value is greater than 10 to the power of 9, so it is considered turbulent. So 0.10 GRPR is equal to 1.54 into 10 to the power of 10 into whole power 1 by 3. So after the substituting the values, you may get the Nusselt number, so which is equal to approximately, which is equal to 249. That is the value you find the Nusselt number. After finding the Nusselt number, you have find the heat transfer coefficient. N is equal to, that is HL by K, because in a cylinder the boundary layer is formed along the height or length. So we can consider that is HL by K. Nu is equal to, so 249 is equal to H into L. Already you know that is height is equal to 1.5 meter into K. So in the previous slide, we can find a K in terms of watt per meter degree Celsius. So 0.02894. So 0.02894. So after substituting the values, you may get the heat transfer coefficient, which is equal to 4.7 watt per meter square Kelvin. Okay. Otherwise, you may substitute the K in terms of kilojoule per something also. You can get the value in terms of kilojoule hour meter square degree. Better, you may initially substitute watt per meter Kelvin in a K is equal to watt per meter Kelvin or meter degree Celsius. We can get the 4.7. Then after finding the heat transfer coefficient, you have to find the rate of heat loss. So it is equal, from the Newton's law of cooling, Q is equal to, that is HA into delta T. Here A represents that is called as a surface area. So H into surface area of cylinder is pi D into L into delta T is equal to TW minus what? T infinity. Here H you already find that is equal to 4.7 into pi into, here D diameter you know that is 180 mm, so 0.180 into length, that is equal to 1.5. Wall temperature, which is equal to 100 degrees Celsius, ambient temperature is equal to 20 degrees Celsius, so 100 minus 20. Okay, then after substituting this value, you may get the Q, which is equal to 325.71 watts. This is the actual heat transfer from this cylinder. The surface temperature is equal to 100. Air temperature that is equal to 20 degrees Celsius. It's having a height of, say, that is 1.5 meter and diameter of, that is a 0.180 meter. So this is the heat loss by the uh, cylinder during the free convection. Okay, thank you. But here you note that the main critical thing is in the problem, value, that is some value is given. This value is enough to solve the problem, but we need a Prandtl number. So Prandtl number, we have a formula to find the Prandtl number. We find the Prandtl number. Almost these values and the values that are available in the data book at 60 degrees Celsius are similar. So you no need to worry about that. And then second one is the K is given in terms of kilojoule per meter hour degree Celsius. We can convert it into watt per meter degree Celsius. So the two complicated things are available in this problem. In many cases of heat transfer problems, the property values are given in the problem itself. You no need to find the property from the data book. Only complicated thing is they have some unit conversion. Okay. Instead of direct giving of Prandtl number, they are giving a density, kinematic viscosity, and some thermal conductivity also. So this formula you know that because many problem we directly take a Prandtl number from the data book. So in some cases we need this formula, so you don't forget this formula. Okay, thank you.